Some quick applications of first order differential equations. The first one is about exponential growth and decay problem. Radium disintegrates according to differential equation dy dt equals ky, where y is the amount of radium at any given time, t, and if the half-life of radium is 1600 years, what percentage of the radium will remain in the given sample after 800? So this is kind of like a biology type of problem. So half-life means after 1600 years, half of the original amount disintegrates up in the air, so you'll have like half of the amount left. So if we decide to let's say, y sub 0 to represent, let's say, initial amount. So y sub 0 here represents the initial amount of the radium at time 0. So 1600 years later, half of it is left. So the question is, after 800 years, what percentage of this initial amount will be left? So if you solve dy, separate the variables, dy over y equals kt, so you get this, exponentiate, you get this. Let e to the c1 to be c, so impose the first initial condition at time 0, y is y sub 0, so you end up with c is equal to y sub 0. So now the mathematical model looks like this. On the other hand, after 1600 years, then y will be equal to y0 over 2. That means that's what the definition of half-life is. So you impose that in this mathematical model or equation, and you get k is equal to natural log of 1/2 over 1600. So now that we know c is y sub 0, k is natural log of 1/2 over 1600. Now we have the complete mathematical model, so we can predict the future. So the question is, after 800 years, what amount of what percentage of the initial amount will remain? Well, if we just go back here and replace the t with 800 and work this out, you get 0.707 y sub 0, which that means 70.7% of the initial amount will remain. Next problem is chemical engineering type of problem. So these are called mixture problem or mixing problem. The tank initially contains 600 liters of solution in which it's dissolved 1500 grams of chemicals. So the tank initially has 600 liters of solution with 1500 grams of chemical. The solution containing 5 grams per liter of the chemical flows into the tank at the rate of 6 liters per minute. So that means this 5 grams per liter is the concentration. So C1 is the concentration of the solution, which is pouring into the tank from the inlet. And it's at this speed, it pours into the tank, which is 6 liters per minute. It's well stirred, and then it flows out at the rate of 3 liters per minute. Notice the concentration of the fluid coming out of the tank is not fixed, because it all depends how much solution you pour in. The concentration varies. And the concentration in the outlet is amount divided by what? Volume. So this would be like so many gram per liter. Okay, so we got C1 equals 5 gram per liter. Rate in is 6 liter per minute. R out is 3 liter per minute, and C2 is variable. Okay, so initial amount of solution is 600. Initial amount of chemical is 1500. So now we have a formula. dV dt, that means how fast the solution changes, is a rate at which the solution goes in minus rate the solution comes out of the tank. So if you solve this, we know R in is 6, R out is 3, so this would be 6 minus 3, dV dt equals 3. When you solve this, you get V is equal to 3t plus C1. So this is amount of volume of the solution at any given time, except now we have to find C1. But remember, initially the tank contained what? 600 liter of solution. Replace the T with 0, V with 600, C becomes 600. So this is the volume of the solution at any given time, which is 3T plus 600 liters. As far as the chemical, the rate of the change in chemicals, dA dt is equal to C1 what? Rn minus C2 R out. Remember, C1 is the concentration of the fluid solution going into the tank. C2 is the concentration of the solution coming out of the tank, except C2 is not fixed. So we got this as 5 and Rn is 6, so 5 times 6 minus 3 times, remember this guy gets to be replaced with A over V. So now we have dA dt equals 30 minus 3A over V, but remember V is equal to 3T plus 600. So if you just move this over, divide, reduce this fraction by 3, you get dA dt plus 1 over T plus 200A equals what? 30. Think of this as a linear first order differential equation. So the integrating factor is what? Mu of T e to the power of what? Positive 1 over T plus 200. So integrating factor would be T plus 200. Multiply both sides of this equation by T plus 200. Integrate the right side. Lo and behold, you get what? 15 times T plus 200 minus 300,000 over T plus 200. So now I can find C2, which is the concentration of the solution coming out of the tank. So that would be A over V. So you got the A, there it is. You got the V, which is the amount of solution. This is the amount of what? Chemicals at any given time in the tank. So evaluate both of these guys at 60 because it says what is the concentration of the chemical in the tank after an hour. 1 hour is 60 minutes. So you would get what? 3.52 gram per liter. So at exactly an hour after this experiment has started, the concentration of the solution coming out of the tank is 3.52 gram per liter. The next one is kind of like a follow-up for this problem, still related. The only problem is up here we were what pouring what a solution with the concentration of 5 gram per liter into the what tank, and then we would mix it and something else comes out of and a mixture would flow out of the outlet. However, sometimes the problem is what would happen if you pour pure water into the tank. Well, that kind of changes the game here because pure water has no concentration. So C1 is 0 kilogram per liter. Okay. And so therefore Rn is what? 5 liters per second. R out is 5 liters per second. So guess what? dV dt is Rn minus R out. So in this case, 5 minus 5 is 0. So V is constant, which is this guy, 1,000 liters. In other words, no matter at what time you measure the volume of the solution in the tank, it's always rain or shine, 1,000 liters. Remember dA dt, the formula is C1R in minus C2R out. Remember C1 was 0 because you had pure water. So this is 0 minus A over 5 times R out was 5 liter per second. So dA dt equals minus 5 over 1,000 A. So if you reduce this by 5, dA, and separate the variables, dA over A equals what? Negative 1 over 200 dt. When you solve, you get this. Initial amount of chemical was 100 kilogram. So impose that condition here so you can get C. And lo and behold, when you replace the C here with 100, you get this. So, and this would be so many kilogram. One thing to notice, which is really interesting, as time approaches infinity, the amount of chemical, which in this case is salt, gets close to zero. What does that mean? That makes perfect sense. The more water you put into the tank, the less saltier the solution gets. As a matter of fact, at some point in infinity land, in long run, there'll be hardly any salt left because it's saturated by the water. Very nice. The next example is about Newton's law of cooling. So this is like mechanical engineering or fluid mechanics type of a problem. So an object whose temperature is 615 Fahrenheit is placed in a room whose temperature is 75 degrees Fahrenheit. At 4 p.m., that's our reference time, the temperature is 135, whereas an hour later, the temperature cools off to 95 degrees Fahrenheit. At what time was the object placed in the room? Remember, when the object was placed in the room, the temperature was 615 degrees Fahrenheit. So the formula for Newton's law of cooling is dT dt minus K equals T minus Tm. Remember, Tm is what? Temperature of the medium, which is the same as temperature of the room temperature or the environment. So in this case, is the room temperature, so it's fixed. So if you replace this guy with 75, the room temperature, separate the variables, solve the equation, you get this. However, at this point, I just want to mention that this C is equal to e to the power of C1. So I let C be equal to e to the C1 after I exponentiate both sides. Well, at time 0, that was at 4 o'clock p.m., the temperature was 135. Impose that condition here, so we can get C is equal to 60. And now the equation looks like this. 1 hour later, the temperature cools off to 95 degrees. So that means T of 1 is 95. Go back here, replace the T with 95, T with 1. K comes up to negative natural log of 1/3. So now the mathematical equation is T equals 75 plus 60 times e to the power of natural log of 1/3 T. So the question is, if T is equal to 615 degrees Fahrenheit, which was how hot it was originally, what was the time at that moment? So replace this T with 615 and solve this equation for T. A little bit of algebra is required. Lo and behold, you get T is equal to -2 hours. Remember, that doesn't make any sense. So the question is, what time did the experiment begin? Well, the reference time was 4 p.m. So -2 means 2 hours before 4 p.m. So the final answer is 2 p.m. Then we have circuit problems. So these are really neat. You can either have RC problems, and that's the type of problem I have here, or RL problem. Before I go over this problem, let me give you a quick background. The amount of voltage change, the change of voltage drop, or across resistor, that's what this guy is. Resistor means it resists the flow of any electric charge, okay? And the unit for resistor is ohms, and it's denoted by this Greek letter. Okay, by Ohm's law, the amount of voltage across these 2 points is I times R, which is current times resistor. This guy is called inductor. Inductor opposes any changes in the current flowing. And the unit for it is Henry, denoted by H. The amount of voltage drop across inductor is L times di dt. Remember, L is the inductor and the unit is Henry. This guy is capacitor. Capacitor stores charges and its unit is farad. And the amount of voltage drop across a capacitor is 1/CQ. Q is what? Is the electric charge, and this is how it's related to the current. So the current I is the rate of change of electric charge with respect to what? Time. So in other words, this would be like coulombs per minute, which is I, and the unit for I is also known as ampere. So now, suppose you have a closed circuit, so it's not open, it's closed. So you have a voltage source, which is like DC. It doesn't change. It doesn't depend on time. It's 100-volt battery. You have a 5-volt watt resistor, and you have a capacitor as 1/50 Fahrenheit. Before we solve this problem, we need to know something called Kirchhoff's second law. Kirchhoff's second law says the sum of the voltages around a closed loop should add up to 0. So what we do, we go around the circuit, and compute the amount of voltages on each of these 3 elements and set it equal to 0. How would you do this? You go, okay, this guy is resistor, so the amount of current is IR, so this would be like 5I. Remember, we're trying to find what? Determine the current I for what? For time greater than or equal to 0. So this is 5I. This guy is what? 1/1/50Q, because that's what the voltage drop across the capacitor is. And then you hit this polarity, which is what? Negative and then positive. So this guy kind of looks like minus 100 equals 0. But if you put the 100 on the other side, so you get 5I plus what? 50Q is equal to 100, correct? But remember what I was equal to. I is dq dt. So if you replace the I with dq dt, notice you get a differential equation in terms of Q. So that kind of looks like what? If you divide both sides by 5, you get this. Do you see it? That kind of looks like a first order linear differential equation. The integrating factor is e to the power of what? Antiderivative of 10 dt, which is e to the 10t. So if you go through the process of solving this, you get q of t equals 2 plus c e to the power of negative 10t. The question is, how do I find c? Notice it says the capacitor is uncharged initially. What does that mean? That means q of 0 is 0 coulomb. So impose that condition in this equation and get c is equal to 2. So if you replace c with equal to what? Negative 2, you get q of t, which is the amount of current, what? Equals 2 minus 2 e to the power of negative 10t. But remember, the idea was find I, and I is what? dq dt. So that would be like what? 20 e to the power of negative t. So that guy goes to 0 when you take the derivative. This guy would be negative 2 times negative 10, which is 20 e to the negative 2t. And this would be so many amperes. And once again, notice, as t approaches infinity, guess what? I, the amount of current, gets close to 0 amp. In other words, the longer this guy stays there, so in a long period of time, eventually what? The current drains out and it gets close to what? Having 0 ampere of current. The last example is about free fall type of problem. Free fall type of problems are type of problems which the only force acting on the object will be what? Gravity, and we're going to assume what? The mass is constant. So there are 2 school of thoughts on this one. One of them is what happens if you don't neglect the air resistance. The other is what if you neglect the air resistance. As a matter of fact, I was going to say there are 2 types of problems regarding the free fall, and these type of problems show up in kinematic analysis of rigid body dynamics. Okay, you know the second law of Newton's for motion is net force acting on a mass is proportional to the acceleration. F is equal to ma. Now, in the first part, it says pretend what? You have an air resistance. Air resistance is falls into the category of drag force. In other words, it reduces the motion of the object. It says right here, pretend the drag force is being proportional to the square of the velocity. So F sub d equals kv squared. I need to find k. That's constant of proportionality. But if you read on, it says what? You have the drag force is 0.48 newtons when the velocity is 1 meter per second. So replace this with 0.48, velocity with 1, k is equal to 0.48. So the drag force is 0.48 v squared. Now, as I said, Fd is the drag force and depends on the size and velocity of the object. If the object is small and you're dealing with low velocities, the drag force is proportional to the velocity. If the object is large, like a football, then the drag force is proportional to the what? V squared, the square of the velocity. And this would be like large objects at high velocity. When we say large, we mean like size of a football. Okay. So now, remember, F was equal to ma, so this would be net force. So here's ma, but what is the net force? Well, you got two forces. One is the gravity, which is negative mg because it's going down. The other one is what? 0.48 v squared, which is the drag force we got here, which is going up. Because remember, these guys always have opposite what? Signs. Because one tries to go down due to the gravity, but air resistance is trying to pull it up. So they have to have opposite what? Signs. So if you remember, the mass was given as 0.4 kilogram. So replace m's with 0.4. Divide both sides by 0.4, you get this. But keep in mind, acceleration is dv dt. And now separate the variables. You have this crazy differential equation where you have to use trig substitution, and I'm not going to do that. It takes forever, and eventually you get the answer. The other half, which is like second half, is easy. What if we neglect the air resistance? If you neglect the air resistance, then what? Then there will be no drag force, so this guy would be 0. So all you have is the net force is only due to the what? Applied to the object is due to the gravity. In other words, ma equals negative mg period. Okay, so because m is constant, so you can divide both sides by m, so a is equal to negative g. But remember, acceleration is how fast the velocity changes. You replace this with dv dt. Solve for v, so you get negative what? 9.8 t plus c1. Remember, we're dealing with metric system. So g is equal to 9.8 meter per second squared. Whereas in English system is what? 32 feet per second squared. So this is what we need here because we're dealing with metric system, because we're dealing with kilograms and meters and so on and so forth. Okay then, so where are we? Now, initial velocity, notice it says find the height to which the ball will rise and the time to reach that height if it is thrown upwards with a velocity of 20 meter per second. That's your initial velocity. In other words, v sub 0 is equal to 20 meter per second. Impose that in this in this function. Find out what c1 is. So I found out c1 is 20. So now I like to find maximum height. How do you find the maximum height? Maximum height achieves when the what? Velocity at that point, at that height is 0. So set the velocity equal to 0, solve for time. So that tells you how long it takes for the ball to reach the maximum height, which in this case is 2.04 seconds. And now Take the antiderivative of this guy. Remember, the velocity is how fast the height is changing. Suppose y represents the height of the ball at any given time. So if I replace here the v, the velocity, with dy dt, which means how fast the height is changing with respect to time, and solve this for what? For y, I get this. Now the question is, what's C2? Looks to me, just by the statement of the problem, the initial height was 0 meter. In other words, the ball was thrown up in the air on the ground level. So C2 is 0. So therefore, this is the height of the ball at any given time, negative 4.9 t squared plus 20 t. Remember, we found out it takes 2.04 seconds for the ball to reach its maximum. Take that 2.04 and substitute here, and you get 20.4 meter. In other words, the maximum height is 20.4 meters, and it occurs, what, 2.04 seconds after the ball has been thrown up in the air. Thank you.